Okay, so where do we leave off? I'm talking about the material derivative. Again, it could just be a whole space of points, like inside of a pipe. You give me a coordinate system. There's a volume of fluid that represents a bunch of points, x, y, z points. We're describing the thing as time. Notice I can always draw a point to that thing, and we'll have a vector there. We'll have a vector there for velocity. And now I can describe the acceleration of the fluid with my material derivative. That's a capital D times the vector field. The vector field is something that describes every single point inside the volume of liquid or pipe. And we get the acceleration of a fluid in terms of the material derivative. We had shorthand, or what this represents, is the time rate of change of the entire vector field. So that would just be if everything changes at the same rate. And then this additional term, and you would have this there as well. So this is something that is unique, or that gives us the nonlinearity that occurs in all of our fluids equations, because this is what is causing the issue. In our differential or acceleration term, it's not just this term that you had from physics 1, the time rate of change of something. Now there's this extra term here. This term is the term itself. So whatever it operates on, it takes information about where it already is. Right? So that's the nonlinearity of all fluids equations, which makes them difficult to solve. It's this extra convective term that's talking about what it's operating on to begin with. So that's sort of just a key thing about all fluids equations is you have to deal with this term right here. It's not just the time rate of change. But already from this material derivative, I just want to get across that you can already tell some things about fluid motion. So if you just look at the operator itself, right, it equaled, take the time rate of change of something, then take what it's going to operate on in the first place, which is sort of strange, and then operate on something. So one thing about fluids that I have in these notes is in terms of just like, you can just take really rough scales or lengths about things. So this is some sort of like dimension like here, it's like a D. You could say this is L, and then there's even one in and out of the board. It could be like wider than it is shorter, but these are just things that you could measure and make some estimated guess on. So there's just something already you can do in terms of this, and it's something called scaling that is important. And I just want to introduce that to you now because I see it so much, and I think people should be introduced to it as soon as possible. So it seems weird, but what you end up doing is instead of an equality, you write this, right, scales as or approximately as. And then you just turn all these things into some sort of characteristic, let's say, time scale. So this is just a value of time. It's 1 over time. This is a differential operator. This is just a fraction. And then remember this term right here, what ended up being, right, is you can have this, it's be a U, and then it'd be an X, because this is the dot product, right? Right, where you had these U's that came out and these V's that came out because of that product rule thing. So with these, right, this is some scale in the X direction. Let's call it that one. This would be some scale in the Y and then some scale in the Z. And these are velocities. So then we could just make another addition of terms where, let's say it looks like this, capital letters. Right, where this is an actual like thing I could measure, where this is like, right, this is the length of the pipe, and this would be a width, and this would be a Z, just some characteristic dimensions you could get. And then what you can do is you can then already simplify this operator. Because if I look for a very, very small instant of time, or very, very fast dynamics, think about a frequency that's really small. So or very large frequency, right? So for very, very small values of time, this number becomes gigantic. And if you couple that with if I look at small velocities, these terms don't end up mattering. So then your material derivative then scales or turns into, right, just sort of your classical, it just is the time derivative. And that's just like what you did in physics. And that's pretty powerful because it allows you to simplify this nasty material derivative thing. And there are other things you can do here. In fact, if all of these velocities are actually really, really big, right, think the same way. Right? If you just think about the size of these numbers, if this is large, like if all the velocities that we're talking about, if it's just extremely fast-moving fluids, then it won't really matter the time scale. So like this term would then drop off. So then the material derivative then just behaves like this term right here. And you can even get the same cases if you have small length scales, some combination of those things. So one extra credit I have is just for you to do that, for you to write out some simplifications of this material derivative based on characteristic scales of a fluid problem. And it's super easy. I mean, it could be as simple as like, right, 1 over t. Let's say you want to model things that are like in the time scales of years. So it's like, that makes this number like just, right, effectively nothing compared to these things. I mean, it also depends on your velocities, but it's just a good way to start reasoning things without doing any calculations. You're just comparing 4 terms in an equation. So I think that's helpful. And everyone should do it more because like there's no real analytical solutions for the total problem of fluids. But when we get to these simplification things, this is where those crossing terms comes out from. It's just looking at terms in this thing and saying what's big and what's small. Okay. So that's one extra credit problem you should do. And I'm going to stop and I'll do another video.